This is the chemistry periodic for week 10, and I'm going to be explaining it today. So let me start. This is the course practice, chapter 2, of the chapter 3, sorry. Okay, so this is chapter 3, okay. There is one question that has a mistake in it, I'll tell you which one, okay. And let's go. So first, which of the following is the correct dot and cross diagram for barium fluoride? Okay, so we know that BaF2 is ionic, and ionic dot cross diagrams have to have these bracket things. You know, they have to have these bracket things, ding 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 ding, with the sign here, whatever. It has to look something like this. It has to have these brackets for it to be correct and ionic. Okay, so if it's ionic, it has to have these brackets. ماشي? So BaF2, they want the correct dot cross diagram. Let's look at our options. So let's look at our options. Okay, we go down, we see, okay, A could be correct, okay, B might be correct, C is definitely wrong, D is definitely wrong, E might be correct. Okay, then we start looking at the signs. Okay, so we have to go to our periodic table and see. BA gives me what? BA is, where is BA? Oh my god, oh, okay, BA is here. BA is BA2 plus. Okay, so we go back here. We know that BA is BA2 plus. And we know that F is F minus. Okay, so we crisscross and we get BaF2. So it's correct. So if it's BA2 plus, it has to look like this. Okay. And since we're donating two electrons, okay, and we have two Fs, ماشي, so one electron will go to each of our Fs. So we're only going to have one cross on each. Does the other one have only one cross? Yeah, okay. So it should be A. A should be the correct one, and A is the correct one. Okay? So it should look like this. We have our BA, we have our 2 plus. Since we have BaF2 and BA is 2 plus, it will what's it called? The BA, which is the electron donor, will give out one of its two electrons to each of the Fs. So there are two Fs, and this one will lose two electrons. It's losing two electrons, so one here, it will lose both of the electrons. Okay? Number 2. Which of the following is the correct dot cross diagram for beryllium? Same thing here. So let's go back here to BE. Where is BE? Let's see if we can find BE. And BE is at the top of the group, BE2 plus. Okay? So we go here, it's BE2 plus, and it's F minus. When we do crisscross, we'll get BeF2. So crisscross is just we put this number here and this number here. This number is 2, so we put 2 here. This number is 1, so we put 1 here. So it's BeF2. Okay? When we got the BeF2, we know that there has to be two Fs. So this one is looking right so far. Okay? It has to have the minus sign. It has the minus sign. This one has to have the plus sign. It has the plus sign. Okay? And it has to have one cross. Why only one cross? Because there are two Fs. And if this one only loses two electrons, it will distribute one electron for one F and the other electron for the other F. Okay? By the way, oh, sorry. Yeah, this is the question that's wrong, by the way, guys. So it's they said that B is the correct answer, which is completely wrong, because B would be for a covalent bond. B looks like covalent bonding, because the covalent bonding has these like circles that connect with each other and the dot cross in between. B is completely wrong. C is wrong because it's not F2 minus, it's F minus, and there are two Fs. Okay, the charge isn't 2 minus, so that's wrong. Okay, D is wrong, it's covalent. E is wrong because it's a covalent. Okay, so A is the correct one. Okay, number 3, what is the electron configuration of the metal? When you see this, guys, don't panic. Listen, it's just like that one. Okay, remember the one that we were just doing, BeF2 whatever. Okay, BeF2. Okay, this is the same thing. You have 2, you have Cl, and it's a minus. Just like you had 2, you had F, and it was a minus. So the same rules should apply for both. Okay, now you have X. Okay, X, for it to have a plus here and give a minus here and still give 2. So they want the charge of this X, It's a positive charge, okay? They don't know what it is, it's a question mark, okay? That will give you 2 atoms of Cl, and each of those 2 atoms will have a minus. So how many electrons does it have to distribute? There are 2 Cl's and each of them has a minus. So if each of them has a minus and there are 2 of them, that means 2 electrons were given to it. 1 electron for each Cl. That means the charge here is 2. So it's X2 plus. Now, which one out of these 5 electron configurations can it remove 2 and still end up with a full valence shell? A full valence shell is what? 8 electrons. Let's see. If we give 2, it will become 2, 7. 8, it's not 8 electrons, it's wrong. If we give 2, it will become 2, 8, 6. That's wrong. Here, if we give 2, it's 2 and 8. 8 is a full valence shell, that's why it's correct. 2, 6, it will become 2, 4, that's wrong. 2, 7, it will become 2, 5, that's wrong. Why are we removing 2? Because it's 2 plus. 2 plus means it lost 2. That's why we're removing 2 to see which one is correct. We have to remove 2 and end up with a full valence shell. Number 4. Which of the following conditions are needed for coordinate bonding? Okay, so coordinate bonding is basically adding up electrons together, okay? Like it's dative bonding. It's called dative bonding, okay? It's another word for dative bonding. You have to memorize the conditions for this. So it has to have 1 electron donor that has at least 1 pair of electrons to donate. Okay, it has to have at least 1 lone pair of electrons, ماشي? And an electron pair acceptor that has an unfilled orbital. Okay, so it has to have an acceptor that has an unfilled orbital, and it has to have a donor that has at least 1 lone pair of electrons that it can donate. Okay, that's how coordinate bonding happens. ماشي? Now, which of the following structures have a coordinate bond? Guys, listen. For this type of question, I don't suggest that you understand it really, because I'm getting confused trying to understand it, and it's a bit of a hassle to understand these. You can just memorize them. I'll give them to you right now if I can find them in my damn copybook, because I did write them in my copybook. I'll give you them. Okay, you guys just have to memorize them. Memorize which ones form coordinate bonding. Wait, give me a second. Okay, so I found them. So it's pH4 plus. Okay, NH4 plus, BF4 minus, okay, Al2Cl6, and H3O plus. These are the most common ones, okay? These 5 are the most common ones, okay? If you know these, you should be good for tomorrow in the periodic. You should, maybe they ask us some type of crazy question in which we're going to have to understand why they form coordinate bonding. But I think we have another question here in this quiz. I'm sure that we have another question here in this quiz that I can explain it better to you. So I'll keep the explanation of the coordinate bond for that question. Okay. What is the Lewis structure of CS2? So we should all know how to do Lewis structures by now. So we have C and S2. Carbon is in group, Ya Allah, what group is carbon in? Carbon is in group 4, okay, so carbon is in group 4, ماشي? So we're going to add the valence electrons first, so we go 4, why does that 4 look like that? 4 plus S is in group 6, so we're gonna go 6, and since there are 2 S's, we're gonna go 6 plus 6. We get 4 plus 6 plus 6, 12 plus 4 is 16, and that is our number of valence electrons. That's the number of electrons that should be in our structure. So let's count. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so each line counts as 2 electrons and each dot counts as 1 electron. Okay. So this one has 16 electrons, that's why they chose it. Here, obviously, there's a shortage. 1, 2, 3, 4, 5, 6, 7, 8. That would be wrong. Why is it not 16? It has to have 16. And the other ones all have the wrong number of valence electrons, except for the first one, which is why we choose the first one. Okay? Now, they're asking you, okay, so this is a CS bond. What about the C? How does the CSE bond? So how does a CSE bond compare to a CS bond? Well, the Se bond will be longer, okay? Why is the Se bond longer? If you go to your periodic table here, you find that sulfur, wait, let me show you guys. You find that sulfur and Se are in the same group. If S is above Se, that means S has a smaller radius, because we know from the trends in the periodic table, as you go down a group, atomic radius increases. So if S has a smaller atomic radius, that means that the bond will be shorter because it's more tight, okay? That means the Se will be longer, so the S will be shorter because it's more tight, and the Se will be longer because it's less tight, it has a bigger radius. So that's why the CSE bond is longer than the CS bond, because the atomic radius of selenium is larger than that of sulfur. Which of the following has the largest bond dissociation energy? So guys, the triple bond has the highest, the double bond has the medium, and the single bond has the lowest. N2 is the only one here that forms a triple bond, which is why we choose N2. Now, the bond order of 1 basically means which out of these 5 can only form a single bond. This one can form triple, this one can form double, this one can form single, 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 which is why we choose this. How do you know if it can cause like a triple bond or a single bond? Look at it. مثلا N is in group 5, okay? N is in group 5. How many electrons does it need to get 8? Because we're always trying to get 8, okay? It needs 3 electrons. That means it needs triple, triple bond, okay? That means it needs a triple bond. Do it like that. That's how I memorize it. That's how like I see it. That's how I make sense of it, okay? The number of sigma and pi bonds in CO2. Okay, so we have C, which is in group. First, obviously, when they ask you something like this for sigma and pi, always draw the full Lewis structure. Okay, always make sure you have it fully expanded in front of you. Okay, so like if they give you this CH, remember that there's a CH here. You know, like there's a bond in between them. Don't forget it, because they'll try and trick you. Expand the thing fully in front of you tomorrow. Okay, make sure you have it expanded fully. But here they're telling you to expand it, so you expand it now. So you have CO2. C is in group 1, 2, 3, 4. Okay, so C is in group 4. Yallah. C is in group 4. So there are 4 valence electrons. O is in group 6. So plus 6 equals to 16. Okay, so obviously we're gonna have C in the middle since there are 2 O's. This one's pretty straightforward. Okay, you have C here. You have 16, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. First you fill it out and then you start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, we have 4 extra electrons. So what are we gonna do? We're gonna start double bonding. Bang here, we put it here. Okay, now we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Still not enough. We still have 2 extra. We're gonna remove from here and we're gonna remove from here and we're gonna double bond it. Now let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. Okay? 12. What? Oh, sorry. 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay? It's 16. Okay, so now this is the correct Lewis structure. Why do we not draw here a triple bond? Because O can't triple bond. O can only double bond. So don't do this tomorrow and say, oh, there are well, it's still correct here. It's 2 sigma and 2 pi. You still get the correct answer, but this is wrong. This is the wrong Lewis structure. Okay? Because O can only double bond. Because O is in group 6. So for it to become 8, it needs 2 electrons. So that means it needs only a double bond. That's the maximum it can make. Okay? So don't make that mistake tomorrow. So obviously from the structure that we drew, here, we find that it's 1 sigma 1 pi, 1 sigma 1 pi. As the 1 sigma 1 pi, 1 sigma 1 pi. The one up is pi. It doesn't really matter, to be honest. Okay? So it's 2 sigma 2 pi. Okay? Which of the following has a Lewis structure that is an exception to the octet rule? Okay, so to be an exception to the octet rule, guys, Ya Allah, Ya Rabbi. to be an exception to the... Okay, you have to have an incomplete octet. The incomplete octets, okay, they're like 4 elements, okay? The incomplete octets are BE, B, HE, and H, okay? These are the most common ones, okay? And I think these are the only ones, really. These don't have enough electrons to make a full valence shell. They don't have enough electrons to have 8 valence electrons, okay? They just don't. They don't have electrons. They don't have enough, okay? So they're called electron deficient. ماشي. These are exceptions to the octet rule. Now, anything with with more than enough electrons, like for here PCl5, 1, 2, 3, 4, 5, Cl, 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 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. طب how does P have 10? It's only supposed to be 8, صح? That's why it's an exception. That's why we say these are exceptions to the octet rule. I 3 minus is the same thing. You'll have what's it called? You'll have extra electrons, which is why I 3 minus will be what's it called? An exception to the octet rule. You also have the 10 electrons on the I. ماشي. And yeah, that's pretty much it for here. C is normal, SiCl4 is normal. We're fine with that. Guys, let me also give you the resonating structures while we're here. Okay, let me give you the resonance structures if I can find them as well on my copybook. Where are my resonance structures? Okay. I got my resonance structures. Okay, so guys, I'd say memorize the resonance structures for tomorrow as well. So these are supposed to form resonating. So these form resonating structure. Okay, you have SO2, CH3COO minus. You have NO2 minus. You have NO3 minus. You have HONO2. You have N3 minus. You have CO3 2 minus. You have O3. And you have C6H6. And you have SO4 2 minus. Okay? These are the resonating structures. Know them, memorize them for tomorrow. Okay, number 10. Oh my god. Yes. What is the feature of metallic bonding? It is the metal cations in a sea of delocalized electrons. Okay, it is not network of copper atoms joined by strong covalent bonds. It's metallic bonds. Okay, and the lattice of copper atoms. No, it's a lattice. It is a lattice of Ya Allah, Ya Allah, أخي. Oh my god, why is it not this? What's it called? It's partly true, but it's not detailed enough. So the lattice, it's not a lattice of copper atoms. It's what's it called? It's the electrostatic attraction in between metal cations and delocalized electrons. It's not between the copper atoms. Okay? So it's between the cations and the delocalized electrons. It's not between the copper atoms. Okay? And yeah, so only one. Which of the following has the weakest metallic bonding? Rubidium. Why between these? The rubidium has the smallest amount of electrons, and the more electrons it has, the stronger the metallic bonding. Okay. Number 12. What is the name of NH4,3PO4? It's straightforward, guys. You have to memorize it. It's ammonium phosphate. Okay. For number 13, we have copper 2 sulfate exists as blue crystal in its hydrate. Okay, so guys, this one is easy. What they only want X here. All they're asking for is X here. Okay. So what I do is I take this number and I'd minus it from the mass of this, from the molar mass of this. So like I can get rid of this, like برتاح منها يعني. Okay. So we have so we have 249.5 minus 63.5. Guys, get your calculator out. 63.5. Okay. Plus the 32 plus 4 times 16. Okay. That's 159.5. Now if we minus it by 249.5, we will get 90. Okay, so we got 90. Now, the 90 is left for the H2O. Now, what's the mass of the H2O? H has 1, so 2 H's have 2. Plus O has 16, and there's only one O, so 16. 2 plus 16 are 18. Now, there is 90 left for this 18. We divide them. 90 divided by 18 gives you 5. So X equals to 5. Bing. Okay, so let's see. A is a metal, A is a metal, B is a metal, C is a non-metal. Non-metal. Okay. Don't look at it as A with C, A with A, C and C. No. Look at it. Okay, so they're talking about A and C. Look at it as a metal with a non-metal. Metal with non-metal, what is it? Ionic bonding. Always metal, non-metal, ionic bonding. A with A. Metal, metal. Metal with metal is what? Metallic bonding. C with C. Non-metal with non-metal, always covalent bonding. That's how you look at it. You don't look at it as C with C. No. You look at it as metal, non-metal, metal, metal, non-metal, non-metal. Okay? The number of ions or atoms surrounding an ion or atom in a crystal lattice is called coordination number. What do they mean by this? مثلا I have Na here. Okay? And I have Cl 1, 2, 3, 4, 5, 6. Okay? The number of atoms around the Na is the coordination number. So how many do I have? 1, 2, 3, 4, 5, 6. That's the coordination number. Okay? Okay, this is pretty straightforward. Anything that is horizontal is a sigma bond. Anything that is vertical is a pi bond. Okay, so these are horizontal sigma bond, vertical pi bond, horizontal sigma bond. Okay, so here is the coordinate bond actually. Okay, so you see here that B and N form a coordinate bond with each other. Okay, why? How do you know this? Look here at this. You find that these two dots aren't a dot cross. They're two dots. Means they're added together. They're dative bonding. Okay, what does this mean? This means that the B doesn't have it has space. It means that it has space for one electron pair to be added to it. Okay, so like it's an electron acceptor that has space. It's deficient. B is one of the deficient atoms. B, Be, H, He, B is one of the deficient atoms. Okay, so that's our first sign. Now N has a lone pair. N does have an extra lone pair of electrons that it can give to the what's it called? To the B. To the B. It has what's it called? Wait, other way around. Sorry. N has space for it to take. ماشي? Like N has space for it to take. Allah, how am I going to explain this? Okay, wait. Let's go to the periodic table. Okay, periodic table here. Where is it? B. What are they talking about? B. Boron. Boron has 5 electrons. Okay, it's electron deficient. ماشي? So if it is electron deficient, تمام, that means it satisfies one of the conditions for coordinate bonding. Okay, then you have N has lone pairs. Okay, it has extra lone pairs, which means that it satisfies the second condition. You remember here, where is the condition, ya Allah? Define dative bond here. Okay, an electron donor that must have at least one lone pair of electrons, an electron donor that has at least one lone pair of electrons. B is an electron donor that has one lone pair of electrons, and an electron pair acceptor that has an unfilled orbital. Electron pair acceptor that has an unfilled orbital. What do they mean by that? Okay, so forget everything that I've said. Okay, forget everything that I told you. Okay, look here. At least one lone pair of electrons. N has a lone pair of electrons. Look, and here it has a lone pair of electrons. It's N7. So if you like drew it here. It had 1, 2, then 1, 2, 1, 2, 3, 4, 5, 6, 7. It has a lone pair of electrons. Has a lone pair of the electrons. Okay, there is a lone pair of electrons. That means it satisfies one of the conditions. And then B خبصت. What the hell? Okay, so guys, my bad. I lost myself. Okay, I genuinely lost myself. My bad. Yeah. Okay, so basically the dative bond is electron pair acceptor with an unfilled orbital and an electron donor with at least one lone pair of electron. We have that here. N is an electron pair acceptor, meaning it makes a minus charge, okay, with an unfilled orbital. It's unfilled, okay, there's still space in its orbital. And B has a lone pair of electrons, okay, it has a lone pair of electrons that it can donate to N. ماشي? And that's why I formed the dative bond. It was that simple. I just got confused. Okay, so the most stable form of H2 exists at, okay, so guys, for this graph I'm going to make it like as simple as possible. Okay, forget everything. The only thing they're going to ask you is this, so just understand this. The most stable form is always at the bottom. The most stable form is always at the bottom, so it's at B. The H2 molecule forms as energy is released. Any molecule that forms, energy has to be released, okay? Energy has to be released. ماشي? So energy is always released. Then the attractive and repulsive forces are balanced at B. Attractive and repulsive forces are always balanced at the lowest point, so at B. The bond length is measured at B. The bond length is always measured at the lowest point, so you always take it at the lowest point. The magnitude of the bond energy. The bond energy is always measured at the lowest point, so you take the magnitude of the bond energy at the lowest point. The magnitude is always in absolute value, so you get positive 436. Whatever. Okay. Number 19. Okay, so for this one, it's a little bit confusing. It's not that bad. So they're asking us to compare between H2, N2, and O2. So we have H2, N2, O2. Okay. This is the intermolecular distance. So this is intermolecular distance. And as you go to the right, it increases. Okay. And here is the potential energy. So the amount of energy in the bonds. Okay. H has a single bond. Okay. Which means it's supposed to be the longest, right? But here they said that the graph of H2 is the first one. How do we know that this is the graph of H2? First and foremost, it has the lowest bond association energy. It has the lowest potential energy. If you see here, N2 makes a triple bond and O2 makes a double bond. The deeper you go, the deeper that you go, okay, what's it called? The more the energy you have, which is why graph 2 is N2, okay? Graph 1 is H2 because even though that N2 is supposed to be the smallest one, because of just how tiny H2 is, okay, because it doesn't need what's it called, it doesn't have a full octet and whatever, 8 electrons or more. It has like, it's literally, H is so small, okay, it has one valence electron, okay, what's it called, شو اسمه, it has one electron. H has one electron, okay, which is why it's the smallest one here, which is why it's the first one with the lowest bond association energy. But then the second one, then we start looking at it normally. The second one, the graph 2 is for N2. We all know that the triple bond is the shortest bond, so 2 has to be shorter than 3 because 3 is O, and O makes a double bond, okay. So what's it called, and obviously the triple bond is stronger, so we go deeper, which is why graph 2 is for N2 and graph 3 is for O2. Okay, but then we go number 20. Here it's pretty straightforward, okay. You just minus the 11.9 from the 2.4, and what do you get? 11.9 minus 2.4, and you get 14.3. Okay, that's the mass. Then you divide it by the molar mass of chlorine, which is 35.5. So you divide it by 35.5, and you'll get 0.4. What? 11.9 minus 2.4. Oh, sorry, that's 9.5. Yeah, my bad. Okay, 9.5 divided by 35.5 equals to 0.2676, which is 0.268. 0.268. Okay, so my bad. Okay, so those are the moles of the HADA. Those are the moles of Cl. Let's find the moles of aluminum so we can find the empirical formula. So let's find the moles of aluminum. Aluminum has 2.4 grams. It's divided by 27, which is the molar mass. And you get 0.088888, whatever. Let's keep it to three significant figures. So 0.089. Okay. The smaller of these two is 0.268. So we're going to divide it by 0.268. Okay. To get what's it called? Oh no, sorry. The smaller one between these two is what's it called? The 0.089, which is why we're gonna divide it by 0.089. Sorry, my bad. So we divide by 0.089. Okay, divide by 0.089. Okay, this gets 1. 0.0268. 0.268 divided by 0.089 gives you 3. Okay, so 3.01. But if it's 3.0, okay, we 3.0 something, we can keep it as 3. Okay, so what's it called? So it's then, so this is the Al and this is the Cl, so it's AlCl3. AlCl3. Okay. The composition by mass of compound Z, guys, this is pretty straightforward. Okay, you do the 45.5 divided by 12. You do this divided by 1, and you do this divided by 16. Okay, you just take each percentage and you divide it by the molar mass of that element. Okay, then you get the answers. The answers are let's say X, Y, and Z. The smallest one, we divide by the smallest one. So let's say the smallest one is Z. You divide by Z, you divide by Z, you divide by Z. Okay, whatever. When you divide, you'll get this answer in the end. Okay, so you'll get 2 for C, 4 for H, and 1 for O. Okay, that means O had the smallest one. So yeah, I was actually right. Somehow I actually guessed that right. Okay, you'll divide everything by O. Okay, you'll divide it by Z, or you'll get C2H4O. Okay, and then after you get C2H4O, they say that the molecular mass of compound Z is 88. Okay, what does that mean? So the molecular mass is 88. Let's find the mass here of the empirical formula. C has a molar mass of 12, so 12 plus 12. H4 has a molar mass of 1, but there's 4, so we add 4. So 24 plus 4 is 28. Then O has 16, so we add 16. 28 plus 16 equals to 44. So this is 44. How does 44 become 88? We multiply by 2. So you multiply everything here by 2. So C, 2 becomes 4, 4 becomes 8, 1 becomes 2. Okay, here is pretty straightforward. You have to memorize it. Okay, oxygen difluoride OF2, manganese 3 chloride, this means MnCl3, calcium hydroxide CaOH2, lithium hydrogen carbonate. You literally do it. Literally. What am I saying? You say lithium hydrogen carbonate. Okay. Okay, no, this one is important. Okay, I have to actually solve this. How am I gonna explain this? Okay. So guys, we're gonna go for the moles. Okay, we're gonna go find moles here, just like we did a few questions back. Okay, so let's find the moles to find the empirical formula. Let's see. So we find the moles of CO2 by going 0.44 divided by the molar mass of CO2, which is 44. But we're only interested in C. Okay, keep that in mind. We're only interested in C. 0.44 divided by 44. Okay, 0.44 divided by 44. You get 0.01. Okay, that's for C. Okay, then for H has 0.27, then divided by 1, 0.27. Okay, but keep in mind, sorry, I got confused. Okay, keep in mind that this 0.27 is for H2O, and since there are two H's and we only want H, we're gonna multiply this by 2. Okay, we're gonna multiply this by 2. So we're gonna go 0.27 divided by the molar mass of 18, which the molar mass of H2O, which is 18, all multiplied by 2, okay, because there's H2 here. You get what do you get? 0.03 ماشي. And then for moles of NH3 the same thing. So NH3, N is already like balanced, okay. We only have one N and we only have N here, okay, so we keep it just as N. 0.085, we go 0.085 divided by 17, which is the molar mass of NH3. 0.085 divided by 17 gives you, what does it give you? 0.005. 0.005, okay. So now I have 0.005, 0.001 and 0.003. You add all of those together, okay, and then you subtract them from the total. The total, which is 0.03. Subtract them from the total. You'll get 0.06. This 0.06 is for what? For the oxygen, the thing that's left. So oxygen has 0.06, H has 0.03, C has 0.01, 0.01, and N has 0.05. N has 0.05. N has 0.05. Okay. 0.05. Okay, sorry guys, my bad. It's 0.005. Okay. So then you just divide everything by 0.05, divide everything by 0.05. We will end up with C as 2, H as 6, O as 1, and then N as 1. Okay, so C2H6ON. Okay, that's what we'll end up with. 24. Okay, guys, basically, this is an anhydrous compound because there's no H2O. This one is a hydrated compound because there is H2O. Okay, and the water that we added to this anhydrous compound is called the water of crystallization. Okay, and that's it. I'll be doing the next course practice soon, inshallah. Okay, so see you in a while.